Thanks so much for being here tonight. My name's Hannah Barkley, and I'm a coral reef oceanographer with NOAA's Pacific Islands Fisheries Science Center. And the work that I'm presenting tonight represents a collaboration between NOAA and my former lab at Woods Hole Oceanographic Institution, and represents the work of very many people from both institutions. And tonight I want to tell you a story about one of my favorite places on the planet, which is a place that few people have ever heard of, and even fewer have ever visited, but which I think tells one of the most compelling stories I know of the impacts of climate change on coral reef ecosystem health. Climate change is the single biggest global threat to coral reefs. Increasing carbon dioxide concentrations in the atmosphere from the burning of fossil fuels and deforestation are increasing concentrations of this greenhouse gas at an unprecedented rate. Shown here is a concentration of carbon dioxide gas in the atmosphere for the past several hundred thousand years. And what this time series shows is that while concentrations of carbon dioxide do vary through time and oscillate, go up and down, we're currently at an 800,000 year maximum of carbon dioxide concentrations. If I zoom in on just the past few decades, so from about 1960 to a little bit before the present day, we see that there's been a steady increase in the concentration of this gas, where at the beginning of this record in 1960, concentrations were at about 320 parts per million. And they've risen steadily to present day concentrations at and now exceeding 400 parts per million. This increase of carbon dioxide gas in the atmosphere is changing the physical and chemical conditions of the nearshore tropical reef environments in which corals live. Carbon dioxide is a greenhouse gas, which means that as it's emitted into the atmosphere, it forms a blanket and traps heat, causing the atmosphere and oceans to warm. Shown here again is the atmospheric CO2 time series in red, and now beneath it is a time series of ocean temperatures. It's plotted as sea surface temperature anomalies, which are the difference between a measured temperature and the long-term average. And areas shaded in red are time periods where temperatures were warmer than normal, and areas shaded in blue are those that are cooler. And as we've seen the steady decline in atmospheric carbon dioxide concentrations over the past 6 decades or so, there's been a steady increase also in ocean temperatures. This underlying baseline trend is punctuated by the occurrence of several episodic high temperature events, such as those that occurred here in 1998 and 2010. And these are largely driven by El Nino or other large-scale climate processes. It's these episodic high temperature events superimposed on a baseline warming trend that have the biggest impacts for coral reef health. Increasing temperatures driven by the increase of carbon dioxide in the atmosphere are a problem for coral reefs because they drive a process known as coral bleaching. Coral bleaching occurs because the symbiosis that exists between the coral animal and the photosynthetic algae living within their tissues is incredibly temperature sensitive. In a healthy symbiosis, the corals provide their algae with a place to live, and in return, the algae conduct photosynthesis and transfer the products of photosynthesis, the organic carbons and sugars, to their coral host, providing them with their major source of food. However, this relationship breaks down under high temperatures, and when temperatures start to rise, even about a degree or so above normal, above what corals are used to, the corals get stressed and expel their algae from their tissue. The expulsion of these pigmented algae, which give the coral their color, reveal the underlying white coral skeleton, hence the term coral bleaching. Now, corals can recover from bleaching if the temperature stress subsides or if the corals are able to reacquire algae from the water column. But if temperature stress is prolonged, this can cause corals to starve because they've lost their major source of food and ultimately die. Coral bleaching. Yeah, do you have a question?
You talked about the coral expelling the algae.
Mm-hmm.
For years, there was discussions of whether the algae were leaving or the corals were expelling.
Mm-hmm.
You said as a fact that they're expelling, or just as the result?
I believe what's the latest research I've heard is that they're actually producing reactive oxygen species, which are toxic, and that causes the algae to yeah. So coral bleaching is a global problem as the frequency and intensity of bleaching events and these warm periods has continued to occur. More and more reefs globally have been observed to have huge bleaching events. And so this is a global map of bleaching events in the past few decades. And these points in red show places where high levels of bleaching, greater than 50%, have been observed to occur in just the past few decades. And so this is becoming a global problem. It's had widespread and lasting impacts for coral reefs in every single ocean. At NOAA, we're seeking to understand the impacts of coral bleaching on coral reef health, to first of all monitor and document these events as they're occurring, to understand the potential for recovery and resilience of coral ecosystems to the impacts of temperature and bleaching, and to project the future of coral reefs under a rapidly changing climate. As we've conducted our studies of coral bleaching, one of the most compelling stories that we've seen so far has come from the island of Jarvis, which is a tiny island located dead on the equator in the central Pacific. It's about 1,500 miles dead south of Oahu, and it's part of the Pacific Remote Islands Marine National Monument, which means that it's largely shielded from direct human impacts such as fishing. And it also has severely limited access, although admittedly it's so remote that few people dare to venture here at all. And in fact, it takes us about 5 days sailing from Honolulu to even reach this island. But what this means is that Jarvis is in relatively pristine condition. It's untouched by direct human impacts that we see in a lot of our reefs around the coast. And so it becomes a compelling place to look at the impacts of climate in the absence of other human stressors. Zooming in on the island itself, Jarvis is a really tiny island. It's only about a mile north to south and only a little bit wider east to west. Its max elevation is about 23 feet above sea level. It's uninhabited, it has no source of fresh water and no trees, and frequently no vegetation at all. And the only permanent colonizers of this island are hundreds of nesting seabirds, an assortment of geckos, and an impressive amount of hermit crabs. And admittedly, this is really far from what my idea of Pacific paradise should look like. And while it's slightly underwhelming at the surface, the real treasure of Jarvis is what lies beneath the ocean surface. By virtue of Jarvis's position dead on the equator, it lies right at the epicenter of some of the most turbulent and dynamic variability in the global oceans. And the major source of this variability is the El Nino Southern Oscillation, or ENSO, which is a periodic oscillation in wind and temperature conditions that affect the tropical Pacific. And to understand the impact of El Nino at Jarvis, the story starts with the trade winds, which we're all pretty intimately familiar with living here, but the trade winds generally move in an east to west direction across the Pacific. And to understand how the trade winds affect Jarvis, we're going to change perspective slightly. So again, we're looking at this map, looking down on the Earth on top. So we have South America and Peru to the east on the right, and then Indonesia and to the west on the left. And now on this bottom image, we're now looking at a slice of the equator as if we were standing at Antarctica and looking north. So now we have Peru to the east on the right, and then Indonesia to the west on the left. And this is the ocean and the atmosphere. And so the trade winds are blowing east to west from Peru towards Indonesia. And when the trade winds reach Southeast Asia, they hit land and then rise. And air that's rising dumps moisture. And so this is why this area is so rainy and cloudy all the time, because of this rising air. The air then returns east at elevation all the way back to the coast of South America and then moves downward, completing this circulation cell. And this is known as Walker circulation, or a Walker cell. And the same pattern that's happening in the atmosphere also happens in the oceans. As the trade winds move from east to west, they push water along with them and creating a surface current along the equator. Similar to how when the air hits Indonesia and then moves up, water that hits the coast of Indonesia has nowhere else to go, and then is pushed downward in the process of downwelling. And so we've now accumulated a bunch of water in the west that now needs to somehow get back to the east. And it does so along this deep current known as the equatorial undercurrent, or the EUC, which is about 150 to 200 meters below the surface of the water. And interestingly enough, this current was discovered by longline fishermen who are moving across the equator along this surface current, and noticed that their long lines at depth were actually moving in the opposite direction that they were. And thus they were able to discover that there was this current moving. Do you have a question? The opposite direction.
Why does the trade winds go down?
Down?
And then turn back around.
Like here? Oh, so this is happening at elevation. So this is along the surface, and then this is high up in the air. Yeah, it's driven by this cell that kind of moves them in this direction. And it's driven by changes in temperature and the Earth's motion. So then this equatorial undercurrent's moving all the way to the east, and then when it hits the coast of Peru, it's brought up to the surface in a process known as upwelling, thus completing this circulation pattern in the ocean.
Just repeat how deep the equatorial undercurrent goes.
It's about like 200 meters or so. Yeah, 600 feet. And this pattern of circulation has dramatic consequences for temperatures in the equatorial Pacific. So shown in this map on top is the average ocean temperature of the tropical Pacific. So areas that are in blue are cooler temperatures, about 18 to 20 degrees Celsius, and areas that are red are warmer, so about 29 to 30 degrees Celsius. And as you can imagine, deeper water is much cooler. And so when this deep water comes to the surface in this process of upwelling, it brings with it this very cold water that we can actually see off the coast of South America. And as this water is pushed west along the surface current, you can see this tongue of blue water that's moving across the equator. The water is warmed up by the sun as it's moving from east to west. And so by the time it reaches the west, it's considerably warmer, and it forms this pool of warmer water known as the Western Pacific Warm Pool, or affectionately to climate scientists, the whoop whoop. Yeah?
Along the coast of Peru, coast to coast, the upwelling brings a lot of nutrients to the surface. And then any of them get trapped into the surface current, and the surface current doesn't get trapped close to the coast.
There are nutrients, and that's part of the story. That we'll get there. So by virtue of its position dead on the equator, Jarvis is subject to a process known as topographical upwelling. In other words, it stands dead in the path of this equatorial undercurrent. So as this current is moving at depth from west to east, it slams into the island of Jarvis on the west. And this water that normally is at 150 to 200 meters is rapidly brought to the surface. And so water that we normally see only at depth creates a strange conditions around Jarvis where it's very different from what the surrounding ocean looks like. And so if we zoom in on the western side of Jarvis, so this is again looking at a slice of the equator, and this is the western side of the island. As this equatorial undercurrent water is slamming into the western side, it's upwelled. And the chemical and physical composition of water at depth is very different from what's at the surface. So water that's been at depth hasn't been exposed to the sun for a long time, so it's very cold. And it's also been exposed to biological processes such as respiration, also remineralization and decomposition. And the net result of all these processes is that deep water is very low in pH, and it's also extremely high in nutrients. And so the water that's brought up to the surface around Jarvis is very cold, low pH, and extremely high in nutrients. As this water reaches the surface and is then pushed from east to west, it begins to get warmed by the sun, the nutrients are consumed, and it begins to take on the characteristics of the rest of the ocean. So it's hotter, higher pH, and has lower nutrients. Looking at the actual impact of this upwelling on Jarvis. So we're looking down at Jarvis from the top now, and this image on the left is of temperature around the island, and on the right is total nitrogen and the amount of nutrients in the water. In this temperature plot, the areas that are in blue are lower temperatures, in this case about 24 degrees Celsius, and the areas that are warmer are the reds and oranges up to about 26. And we can actually see, looking at these maps, the influence of this very cold water upwelling on the western side. This area here is much cooler than the surrounding water to the east. We see the same effect looking at total nitrogen concentration, where this area on the west, where this water is being upwelled from depth, has much higher nutrient concentrations than the rest of the island. This is unusual because most coral reefs live in incredibly low nutrient regimes. They're oligotrophic. And so to have these nutrient oases in the middle of the ocean creates unique characteristics for the reef communities living there. As a result, Jarvis coral reefs are spectacular. This image was taken in April of 2015 of the western slope. And these platycorals here are Montipora corals, and they cascade down in an almost waterfall-like pattern on the western side as far as the eye can see. Corals get most of their food from their photosynthetic algae, but they're also able to consume plankton and nutrients. And the increase in nutrient concentrations driven by the upwelling increases the plankton concentrations around these islands, so the corals are able to do really, really well. The increase in nutrient concentrations on the plankton that feed on them also have repercussions for the rest of the food web. One creature that really loves these high plankton concentrations are the manta rays, and they're some of my favorite creatures at Jarvis. I like this image because even though it's a perhaps not that great photo of a manta ray, you can actually see the plankton in this photo as these little particulate brown dots. And swimming on the western side of Jarvis when the upwelling is strong is almost like swimming in a soup of plankton. You can almost just feel them hitting your face because there's so much productivity in the water. And in fact, it's almost hard to see like people near you because there's just so much going on. And because of this immense productivity, this propagates even further up the food web as well. And my favorite wildlife sighting at Jarvis so far was these scalloped hammerhead sharks. And this photo was taken in 2016 when a school of about 50 to 100 of them were spotted off the western side of the island. And they're a little wary of people, so they sort of patrol right at the edge of eye level, which is slightly creepy, but also really cool. And one of the really neat things about Jarvis is that it actually has an inverted trophic pyramid. And so most places, like most terrestrial systems, have more creatures at the bottom of the food web than they do at the top. There's a lot more plant material, and then fewer and fewer predators moving up the food chain. But it's actually the opposite at Jarvis. There's so much productivity in the water that there's more sharks than there are the prey items that they feed on. And so this is an incredibly rich and diverse ecosystem driven by the oceanographic conditions that occur in these places in the equator, along the equator. So I've described what could probably be called an average state of things at Jarvis. But the truth is at Jarvis, things are rarely ever average because conditions change dramatically with phases of the El Nino Southern Oscillation. I've described what could be considered a neutral phase, but there's also two other phases, La Nina, or the cooling period, and El Nino, or the warming period. What happens during La Nina is that this entire system strengthens. So the trade winds start to accelerate, and this drives a rapid increase in the motion of this cell. This causes, as the trade winds push more water, a strengthening of this equatorial undercurrent and really strong upwelling at Jarvis, which brings even more really cold, low pH, high nutrient water to the surface. The opposite happens during El Nino, or during a warming phase, when the trade winds slacken and really don't drive the surface current as strongly from east to west. Instead, westerly winds, which are winds moving from the west to east, start to push the whoop whoop, or the warm pool of water that's normally sitting in the west, more towards the central Pacific, right where Jarvis is. In addition to that, because the trade winds aren't driving this circulation pattern, the equatorial undercurrent weakens and the upwelling completely shuts down. And so that source of water coming up from the deep to the western side of Jarvis basically no longer exists during periods of El Nino. And so as you can imagine, this causes temperatures to rise dramatically, as well as nutrient concentrations to fall. We can see the dramatic swings that El Nino variability causes in ocean temperature by looking at long-term temperature records. And shown here is a long-term time series from 1982 to about 2016 of sea surface temperature records at Jarvis. And this gray time series comes from a satellite. And then the red and blue time series come from loggers that we've been deploying at Jarvis for the past 2 decades or so. And the red is from the non-upwelling side, the east side, and the blue is from the west side, or the upwelling side. And you can actually see the influence of upwelling in these time series, where the blue time series, where the water's constantly coming up, the cold water's coming up from the deep, causes temperatures to get pretty low, down to about 20 degrees. And moving through this 2-decade time series can really highlights the impact of El Nino on temperatures. And so during periods of La Nina, the cool phase, when upwelling is really strong, temperatures get quite low, down to, in this case, about 20, even below 20 degrees Celsius. And then during phases of El Nino, the hot phase, when upwelling shuts down, temperatures get really warm, reaching as high as 30 and sometimes even above 30 degrees Celsius. And so this is an ocean region marked by incredible extremes in temperature, on the scales of every 4 to 7 years with El Nino. We also see similar patterns in pH and nutrients, depending on how much of this deep water is being upwelled to the surface. So shown on top here are discrete pH samples that our program has been collecting since 2008. And again, the blue points are from the west side, and the red points are from the east side. And during periods of La Nina, the most dramatic La Nina we captured was in 2008. pH is a bit lower because that water, the deep water, is coming up to the surface. And during periods of El Nino, such as in 2015, pH gets a lot higher because that low pH water isn't being upwelled. We see the opposite in nutrient concentrations. During La Nina, when the upwelling is strong, nutrient concentrations are very high as 12 to 16 micromolar. As a basis of comparison, most coral reefs barely have concentrations above 1 micromolar. So this is extremely high compared to most coral reefs worldwide. During El Nino, when the upwelling shuts down, the concentration of nutrients is below our detection limit. And so we see these dramatic changes in temperature and pH and in nitrogen concentrations depending on the phase of El Nino, further highlighting just how turbulent and dynamic these ocean environments are. As climate has continued to change, the frequency and intensity of bleaching and El Nino events has become even more severe. In particular, we've started to see more and more of what we can call super El Nino events, which, as the name implies, are extraordinary in their strength and in their impacts. And 3 super El Nino events have occurred thus far on record. The first in 1982 to 1983, the second in 1997 to 1998, and the third most recently in 2015 to 2016. And this most recent event in 2015 produced some of what may have been the hottest temperatures on record in this region. And shown here is the most recent 2015 event. This image is from January 2016. And what's shown here are degree heating weeks, which are a metric of accumulated thermal stress. They give us an idea of how long temperatures have been hot on the reef. And so by this scale, degree heating 0 and 4 aren't expected to cause any bleaching. That basically is the equivalent of a degree or so warmer than normal on a reef for a month. Degree heating weeks between 4 and 6, these yellows and oranges, are expected to cause moderate bleaching. That's the equivalent of it being hot on a reef from a month to 2 months. Those greater, between 8 and 12, are expected to cause severe bleaching. It's been hot on a reef for 2 to 3 months now. And those greater than 12 are expected to cause catastrophic bleaching and mortality. And so these areas in the browns and purples. At the beginning of 2016, Jarvis was right smack dab in the middle of this big degree heating weeks greater than 20. This means that by this point, it had been more than 3 to 4 degrees Celsius warmer than normal at Jarvis for months. And these conditions should be expected to cause catastrophic bleaching and mortality on the reef. We were fortunate enough that we were able to actually visit Jarvis during this. In the face of these extreme thermal anomalies, what actually happened on the reef? How did it respond to this extreme thermal stress? And so again, this is what Jarvis looked like before this temperature, April 2015, with these platy on the western side. This is what that same reef looked like in November 20. Bleaching had really started once temperatures had been warm for quite a while and bleaching occur. Every single one of these corals is starving. Yeah, go ahead.
So
How do you categorize that? Severe?
This is severe,
That's severe, right?
arguably catastrophic.
Is there any live coral in between the white?
Actually all alive. So when the coral's bleaching, and what these corals are now undergoing is they've expelled their algae. They felt that they've expelled their algae. Even without their algae, the coral is still living.
Our carriers, they still live corals?
Oh no, this is just bare substrate. Yeah. So these corals are currently starving, and they've been now. And we quantified by conducting ecological surveys at 3 different depths. And it showed 5 to 20 meters or so, that's 15 to 60 feet. Bleaching was between 95 and 100%. And it was slightly less at 60 feet, but still at 90+%. And this was across all coral genera. So the coral shown here, the branching Pacillopora, and also the massive corals such as Porites and Favia. Bleaching was widespread across all genera. And so this is severe. We're actually able to return to Jarvis just a few months later in May of 2016. And by that point, we found a coral graveyard. This is a photo of the exact same slope covered in platy corals. It's now been reduced to carbonate rock. The slope the carbonate rock that used to be covered in these platy corals, they've died and have completely been moved by water motion. Here, these are the skeletons, former skeletons of branching corals that are now coated in a layer of algae. And there really just wasn't much left. It was like watching an entire reef die before our eyes. We returned a year later in April 2017, and coral cover still remained low. You can see around here, this sort of coral rubble that persisted. Some corals had recovered. This is a Porites coral that was in and recovered, but overall, cover remained extremely low, even a year and a half after this event. We've been monitoring coral cover and this reef since the early 2000s, and because we have these long-term records of what coral health and coral cover looked like for the past almost 2 decades, we're able to put these events in perspective to see how this dramatic and precipitous looks in the context of these long-term trends. And so shown here is coral cover for Jarvis in red, and then 2 islands also on the equator farther west in the reds. And since 2002, we visited Jarvis every 2 days, and coral cover has remained fairly steady since then at about 25%. Event in 2015, coral cover declined dramatically to less than 1%. There was a small increase in coral cover in 2017. To date, these populations have not recovered. Because we take an ecosystem scale approach to understanding coral bleaching events, we're able to see how the increase in temperature and the coral affects the entire reef ecosystem. And here are just a few of the ecological indices that give us an idea how this entire reef ecosystem responds to stress level. And so fish biomass, which is shown here, the post-bleaching 2016 the reef communities, and we observe a significant fish biomass between 2015 pre-bleaching and 2016 post-bleaching, although this appeared to have recovered slightly in 2017. We saw that in 2015 and 2020, significant increase in sea surface temperature, and that led to a precipitous decline in coral cover. However, the decrease in coral effects for the creatures on the reef who depend on the coral as their source of food. And so as coral cover declined, there were also significant coral-associated fish that depend on these corals. Because the upwelling shut down during the El Nino, significant decrease in nutrient concentrations, which led to a significant decrease in the concentrations of plankton, the biomass of plankton in the oceans. We can look at this in chlorophyll as a proxy. It gives us an idea of just how much plankton is living in the ocean. And we saw a significant decrease in chlorophyll in response to the El Nino event. As you can imagine, a decrease in plankton and in chlorophyll affects the planktivorous fish that depend on plankton as their source of food. The biomass of planktivorous fish also decreased, although once upwelling resumed in 2017, these also appeared to bounce back fairly quickly. Question?
2010, the temperature is up about as high as 16, yet the other measurements don't seem to be affected.
Yeah, so 2010 was actually a moderate El Nino, but this figure here doesn't capture it, but the anomaly that resulted was much less than what happened in.
Do we know why?
In what?
Do we know why?
It's actually a difference in the type of El Nino. So 2010 was what we call a Central Pacific El Nino, or sorry, yeah, a Central Pacific El Nino. And 2015 was an Eastern Pacific El Nino. And the two types have slightly different footprints as to how they affect the temperature in the Pacific. And so the Central Pacific 2010 produced much lower temperature anomalies than the Super El Nino did. So it still was a significant event that caused coral bleaching, but it wasn't as significant, especially in the Central Pacific, as the 2015 was. That's a good observation. So the 2015 to 2016 event was the first time we were able to witness directly the impacts of high temperature at Jarvis. But El Niños have been occurring for decades and probably even for centuries. And every 4 to 7 years, we know that these temperatures swing, that whenever an El Nino occurs, that upwelling shuts down and that temperatures get warm. This is again, looking at a time series of temperature for Jarvis. These are shown as sea surface temperature anomalies. And what this record demonstrates is that at least between 1982, which was the start of the satellite era, to present, that temperatures swing dramatically from up to 3 degrees above normal during all the way down to 3 degrees lower than normal, depending on the cycle of El Nino. And this produces very frequently dramatic temperature stress at Jarvis. And shown in the bars below are degree heating weeks. So again, that metric of accumulated thermal stress. And recall that that degree heating weeks of around 4, so right here on this plot, are expected to cause moderate levels of bleaching. Degree heating weeks greater than 8 are expected to cause severe levels of bleaching, and degree heating weeks even above that are expected to cause even more severe to catastrophic levels of bleaching. And at least 7 times since 1982, degree heating weeks have exceeded 10, 20, even 30 at Jarvis during these El Nino events. And so based purely on temperature alone, on average, every 5 years, Jarvis has experienced temperatures expected to cause catastrophic levels of bleaching. And yet we've never witnessed what happened. What happened to Jarvis in the Super El Nino in 1998? What happened to Jarvis during the Super El Nino in 1982? To date, we haven't been able to really answer this question, and that's because our ability to understand bleaching events has long been constrained to what we've been able to observe as they've occurred. But it's often, and almost for places like Jarvis, impossible to always hit these bleaching events when they happen. And so how do we go back into the past? How do we reconstruct what happened during these El Nino events when temperatures skyrocketed, but no one was actually there to observe what happened? And we've recently been developing a tool to allow us to do this. And to access these records into the past, we've made use of the stories that the corals themselves that live on the reef are telling us. Corals are the tropical ocean's great record keepers, and that's because they sit in the same place for decades, sometimes even for centuries, and all the while record what's going on in the environment around them and how they feel about it. And so we can access the records that they've been preserving to learn something about the past during time periods when no one was there to witness what was happening. And we access these records by taking skeletal biopsies of coral cores. We take them mainly from a coral genus known as Porites, which are these massive yellow colonies. And to do this, we use underwater pneumatic drills that are powered by scuba tanks. And then once we drill into the coral, we extract the coral core, which just looks something like this. And then once we remove it, we plug the hole that's remaining in the colony. and cover it with a cement plug and epoxy. And this prevents long-term damage to the colony. We've gone back months to years after we've collected coral cores, and we found that it causes no long-term damage to the colony. So this isn't something that dooms the coral. And so this is what a coral core looks like. When we're looking at corals out on the reef, only the very top layer, the skin, so to speak, of the coral is alive. And it's made up of a mat of hundreds of thousands of polyps. And so looking at a core, it's this layer here that we call the tissue layer, or the living part. The rest of the coral is actually non-living skeleton made out of calcium carbonate. And so all of this white material beneath the surface skin is skeleton that's been accreted through the past. And corals grow much like trees in that every year that they grow, they put down growth bands or rings. And they put down these growth bands year by year by year and eventually create a record of growth. However, unlike trees, the growth bands that corals produce aren't visible to the naked eye. And so to reveal these growth bands, we CT scan our coral cores. So this is what a CT scan of a coral core looks like. I'm actually always entertained when we CT scan the corals because we use software that's intended for human patients and hospitals. And so they all get patient IDs and have various weights and metrics associated with them. But every year that the coral grows, it puts down two bands, a high density band or a white band and a low density band or a black band. And because we know the date that we collected the coral, which is the top of the core, we're able to go back into the past year by year, step by step, and determine what these growth bands and growth patterns looked like through time. And so what this provides us with is an archive of the past where corals were growing during periods of stress, when temperatures were hot, and therefore recorded how they felt about it. And when we started to look at hundreds and hundreds of coral cores, we noticed something interesting. Every year that high temperatures, that bleaching were known to occur, corals consistently formed high density bands. These are images of what these bands look like. So these are 4 coral cores. The date on top is the date of collection of the coral core. And I've shown every 5 years of the chronology, so every 5 years of this record in yellow. And these red arrows show these high density bands that we call stress bands. And these bands were such a consistent feature of the years in which we knew that high temperatures and bleaching had occurred, that we started to wonder if they could tell us something about bleaching in the past during times when no one was there to witness what was happening. But for a long time, these bands have only been relics preserved in skeletons. And so one of the really neat things about witnessing the 2015 event at Jarvis is that we were able for the first time to really understand the mechanism by which these bands were forming. We know that these stress bands are formed in coral skeletons during periods of starvation, and here's how this mechanism works. This is on the left, an image of a coral core, and on the right, a CT scan of that same coral core. In this case, taken from a healthy colony that was collected in September 2012, so way before the advent of high temperatures and bleaching. This red arrow here points to the bottom of the tissue layer. So again, this is the living portion of the coral, and all of the white beneath it is the non-living skeleton. And the tissue thickness, the thickness of the living layer of Jarvis corals is incredibly thick. It's about 1 centimeter or so in thickness. And Jarvis has some of the richest, fattest tissue of all places we've measured in the Pacific. And we believe that's because there are just so many nutrients and food sources in the water. But the situation changes when conditions get unfavorable for coral growth, when corals get stressed. Here's an image of that same coral at the height of bleaching in November 2015. We can see in this image of the core, the tissue layer has shrunk quite dramatically. I don't know if it appears here, but you can actually almost see where the tissue layer used to be, down here about 1 centimeter down. And as the coral has been subject to high temperatures, it's expelled its algae and has begun to starve. And its stress response is to begin to eat away its own tissue, eating away its own reserves, which causes this living layer to continually shrink and shrink and shrink until it's barely even 1/4 of what it was when it was healthy. As this process is going on, it causes these high density bands at the top of the coral skeleton. And this is occurring because the coral is still growing slightly, even though it's bleached. It's still forming tiny amounts of skeleton, but it's not really able to grow upward as much as it normally is when it's healthy. And so all the skeleton that's put down is done so in this very narrow layer right at the top of the core. And this is what causes these high density bands, these stress bands to form when the coral's starving, when it's eating its own tissue, and when it's bleached. We returned to the same colony about a year and a half later in May 2017, once it had recovered. Fortunately, it had recovered. And again, the upwelling had resumed. There was a lot of food for the coral. So the tissue layer had begun to thicken again, shown by this red arrow here at the bottom of the skeleton. But preserved in the coral, in the skeleton, as the coral had continued to grow, is this high density band. And so even though this coral was able to survive and keep growing after the bleaching event, record of its stress in its skeleton. And so for the first time, we actually witnessed the mechanism of this formation. We saw a coral that went from healthy to bleached to recovered and preserved in its skeletal record evidence of this event. And so what this gives us now is a proxy, a way of understanding when we see these bands in the coral skeletons, what it means. It means these corals were under considerable periods of stress. And so we can apply this record moving farther back down the skeletal record. And so shown here is a much longer coral core. So this was collected in 2012, and it goes all the way back to 1980. We're able to date it based on these annual density bands. This figure on the left shows the density profile of this coral core moving from the top down. And it's shown as a z-score, which is basically the difference between the measured density and the average. So it highlights densities that are much, much higher than normal. With this threshold of a anomalous event as this criteria for forming a stress band, and that just means that the density at this point in the coral is greater than 2 standard deviations above the mean. What this time series highlights is 5 periods that meet our criteria for stress band. It means that the density was much, much higher than the background density of the coral. This qualifies as an anomalous event. Because we're able to date these bands, we can get an idea of when they form. And so what we discovered is the formation of these bands when known El Nino events occurred. And so that's first in 2002 to 2003, during the Super El Nino in 1998, in 1992 to 1993, in 1987 to 88, and the other Super El Nino in 1982 to 1983. And so what this means is that during every single El Nino that Jarvis has experienced, this coral felt high temperatures, it felt stress, it expelled its algae, its tissue thickness shrunk as it bleached, and it preserved this record of stress in its skeleton. Fortunately, this coral was able to recover and to continue to grow, leaving us behind with this record of boom and bust of stress. The interesting thing, though, is that we now have evidence that Jarvis corals feel the heat every time these El Niños happen. But this observation is interesting, given the fact that prior to the bleaching event in 2015, Jarvis was one of the healthiest ecosystems, the healthiest reef systems on the planet. We know that coral cover was at least maintained between 2000 to 2016, despite the fact that an El Nino occurred. We know that fish biomass, that coral cover was extremely high, and that this reef seems to have been able to persist even despite these repeated El Ninos. And so this raises an interesting question. If we know that temperatures got hot and we know that these reefs experienced stress because these corals recorded it, what happened in between each of these times that we measured coral cover? It appears that these corals bleached, but were they able to recover rapidly? And so if that's true, if these corals bleached and were able to recover quickly, this is perhaps indicative of incredible resilience of this system, a reef that experiences stress continuously by virtue of the fact that it's in this dynamic region of the ocean, but appears to keep moving onward. That is until 2015. And so the million-dollar question is now, can Jarvis coral reefs recover? Does the history indicated in the coral cores that these corals experience stress repeatedly and the reef ecosystem seems to recover? tell us that maybe this reef system will be able to recover from this big event in the future, or the hottest temperatures that this reef ever experienced mean that it won't be able to bound back this time, that it's finally met its match, that it's hit the threshold beyond which recovery can't occur. We don't know. So far, recovery has been really slow at Jarvis. We recently got back from another expedition to the island, and coral cover remains really low. However, there have been some encouraging signs of recovery. One of my favorite stories of recovery is this coral that I've affectionately named Lazarus. And this is what it looked like in May 2016. It had, when we got there post-bleaching, we thought that this coral was dead. It is covered in this red algae, and there's no visible tissue remaining on the colony. And we'd pretty much discovered that we pretty much assumed that this was the end of this coral. But to our utter amazement, when we returned a year later in 2017, the coral had almost completely recovered. And all of this skeleton that appeared dead just a year prior had resheeted with new tissue. And this coral was able to continue to grow, and in fact grown about 1 centimeter in between these two time periods. And this is remarkable. It's something that we really haven't ever observed before. But it appears that these corals are able to rebound back from extreme temperature stress and bleaching. What Jarvis really needs now is new recruits. With less than 5%, 1% of its coral cover remaining, the recovery of Jarvis is contingent on the growth of new corals to repopulate the reef. And so far, that recruitment has been slow. There are evidence of small recruits that have been able to establish a foothold on this now coral depauperate reef. But at least for now, the reef hasn't recovered in the past 2 years or so. And so it's my hope that because we have this record of recovery from high temperature in the past, this reef ultimately will recover. But it'll be a grand experiment in the next few years to see what the recovery of this reef ends up looking like. And so with that, I'd like to take any questions, and thank you. Yeah.
There was a super El Nino in 69, 70 around there. But do you have any coral records going back that far or not?
We do. So we have coral records going back into the 1900s, and the work that we're working on now is actually going even beyond the instrumental record, so past 1980. And we see evidence of bleaching in the strong El Ninos in the past, in the 60s, even in the 1930s. And so the evidence that Jarvis is experiencing warm temperatures and bleaching extends well back into the early 1900s. So the high temperatures and bleaching are not a new phenomenon at Jarvis.
I have 2 questions. Is that supposed to be a new small coral colony?
This is a tiny coral colony.
Implying that some corals somewhere were reproducing, making larvae itself?
It's actually one of the big questions we have, is that because the population at Jarvis has been so depleted, where are the new larvae coming from? And there's really 2 places it could come from. The remaining corals, we've only surveyed down to about 100 feet in depth. It's possible that deeper than where we've surveyed, that some corals have survived. There's also the possibility that the recruits could come from, the larvae could come from somewhere else. By virtue of the fact that Jarvis is so remote, there's not many places that larvae can come from. The closest island is Christmas Island in Kiribati, but Christmas Island had considerable bleaching as well.
The other question is, this island, compared to some of the others along the equator, have a lot more zooplankton than coral reefs normally do. Could that perhaps give these corals an extra boost in nourishment and therefore help their recovery in between?
That's a great question. That's actually one of the mechanisms we think might be allowing this rebound to occur, because when these big El Nino events occur, they're often followed by La Ninas. And when La Nina occurs, that causes the really, really strong upwelling. And so a lot of nutrients are being brought to the surface during La Nina, and that would produce more plankton and more food for the reefs. And so one mechanism that we think could be driving this boom and bust cycle is the La Nina that often follows El Nino. Interestingly, there wasn't a La Nina that followed this El Nino. There was not this time around. And so it's possible that the slower than slower recovery could be a artifact of that. Yeah.
My father was a research scientist for University of Hawaii, and he did
Cool.
a lot of research in the Line Islands.
Yeah, yeah.
Christmas and Kitty, the whole.
Yeah.
And he said when the El Niños hit Jarvis, all the birds left. Have you guys noticed anything with the bird life?
Yeah, I think rest you studied that, right? Like the birds.
The paper?
Yeah, the paper. I didn't put it up.
Well, bird life was really affected as well.
Yeah,
Right.
we did. So.
Yeah. Yes.
Is this happening for a week around the island or just east side?
The whole island. Yeah. Yes.
I got a non-horrible question.
Okay.
Jarvis.
Okay.
Around 1940, the military brought some Hawaiians from, I think, Hanauma.
It was Kamehameha, yeah.
And established a little outpost to make sure the enemy knew that it was inhabited.
Mm-hmm.
And they did weather broadcasts, and they got shot at by the Japanese one or two times. Is there any plaque of memorial on Jarvis to commemorate that and all, you know?
I think there might be, but I've never been on the island.
Oh,
Yeah. One of our favorite movies whenever we visit is Under the Jarvis Moon, which tells the story of the early colonizers of the island and the incredible conditions they weathered. I just can't even imagine.
and a final full of lobsters.
Yeah. Yeah.
For the El Nino event, what was the age of that plate coral? Is that have any idea of how old that coral was?
That's one of the big questions we have. Those corals grow very quickly, but we don't really know at Jarvis how quickly they grow. But because that particular genus is one of the more fast-growing corals, it's possible that they are able to rapidly recolonize the reef, like after a bleaching event. That they're the ones who are able to jump on new conditions quickly. Yeah, do you have a question?
Yes, through your research, do you see any evidence that over time coral becomes more resilient to increasing temperatures?
That's a great question. That's something we're trying to answer with our coral core records. At Jarvis, we haven't seen evidence of that, but it's possible in other places that it may be. There's evidence coming out of the Great Barrier Reef right now from coral cores that the resilience of these massive corals to temperature is changing over time. But we're not seeing that here. Yeah, do you have a question?
How do those corals recover so quickly than the other corals around the world?
How do these, like this guy here?
Yeah.
We think it's just because the environment in which these corals live is really favorable for coral recovery. So the fact that after these big bleaching events, they often tend to have a lot of food because the upwelling that brings food to the surface gives them a lot to eat. And so corals that are able to eat a lot are able to recover quickly. Also, the types of corals that live here tend to grow pretty fast. So the platy corals and even these corals here are the kinds that grow really, really fast. They're able to do really, really well post-disturbance. Yeah.
A lot of the places that have been bleaching, afterward, algae come and take over the area. Do you have any effect on Jarvis? Or is it not conducive to algae?
There has been. So when we went in 2016, there was a lot, so immediately after bleaching, there was a lot of like that turf algae kind of covering the reef. Interestingly, what we've started to see now is that most of the reef has been recolonized by crustose coralline algae. And so the predominant cover type now at Jarvis is this crustose algae.
There's a thought that on a lot of coral reefs, the turf algae or whatever kind it is that smothers the coral is kept under control by herbivorous fish. Fish were going away too. Is that part of the issue?
Well, the fish appear to be returning. So the bleaching, when the El Nino conditions occurred, there weren't as many fish. But when the upwelling resumed post El Nino, the fish largely came back, except for the ones that depended very closely on corals. Yeah.
So you're going to Jarvis by ship, big ship, I take it, no vessel, and you anchor it, are there anchorages?
No, we live boat.
Pardon me?
We live boat.
Oh, and so what period of time might you stay?
Usually it's on the order of about 4 days, 4 to 5 days.
There are no airfields on the
No, unfortunately. And I get really seasick, so it's a very long trip for me. Yeah.
I just didn't notice anything. A lot of places where algae comes back, they get filled on by fish, but by sea urchins.
Mm-hmm.
There's a big sea urchin population there.
There's not here. No.
Not at all.
Not the same way there are in the Hawaiian Islands.
Any other questions?
What does it mean to live boat?
Oh, it means you don't anchor. The boat continues to drive around instead of putting down an anchor.
Where do you sign up for your different jobs?
It's pretty spectacular, and I think one of the amazing things about the job I have is getting to go to these places that most people never get the chance to see.